Hello, this is our first lecture for Chapter 10, Vapor and Combined Power Cycles. These power slides were prepared by Professor Carnot and modified by me. Okay, the objectives of this chapter is analyze the vapor power cycles in which the working fluid is alternatively vaporized and condensed, mostly water, but can be any other substance like 134A that do this. I'll repeat the same. So we are going to study this a lot. Analyze power generation coupled with process heating cogeneration. At least we're going to talk about it because we have not described the gas cycle, but we're at least going to talk about it. Investigate ways to modify the Rankine vapor power cycle to increase the efficiency. We're going to talk about reheat and open feed water heaters. Analyze the reheat and generative vapor power cycles and talk about the combined cycles. Okay, let's talk about first about the Carnot cycle. Carnot cycle, as you recall, is the standard. It's the best that we can do. The best machines that we can buy is Carnot cycles. The only problem is that they don't exist. This machine serves as a model and an upper standard, offers a limit of what we can get. If we remember, for a heat engine we need two reservoirs, one cold reservoir and one hot reservoir. From the hot reservoir we are gonna receive the energy necessary for this machine to move. It will create some work, and because of second law we know that we cannot convert all that heat into work, so we need to reject something to the reservoir, low temperature. We can see this here, this Q in, it's at a higher temperature, and this Q out rejects to a lower temperature. This TH and TL are the temperatures of the reservoir. And recall that the Carnot cycle is comprised of four different processes. We start with an isentropic compression. Once that we compress gas, it increases its temperature. It's isentropic, so it goes along this line. Because we are compressing, we are reducing its volume. Then we add energy by transferring heat isothermally. By adding heat isothermally, we increase its volume and we increase its entropy. Then we have an isentropic expansion, in which we reduce its temperature and we increase further its volume, and finally we reject heat isothermally, so we reduce volume again and reduce entropy, and we start over again. So this cycle will give us the best performance for any combination of TL and TH. That means the cold and high temperature, the cold and warm temperature reservoirs. And the simple expression comes from the fact that the area in this diagram is the work done. So we have the net work will be Q in minus Q out, and recall that efficiency is every time it's what we want, is the W net divided by what we need to provide, is Q in. So this is a Carnot cycle, and we would like to repeat this as closely as we can. So we are gonna try to implement it and with vapor. we start facing some problems. The first thing is that we can have isothermal heat transfer by changing phase. Recall that when you have water boiling, it's 100 degrees all the time. So we can solve that requirement of the Carnot cycle by using evaporation for the heat addition and condensing for the heat rejection. Practical problems arise when we try to use a pump, because we will need a pump that has two phases. So we here have a mixture of vapor and liquid, and just remember what happens at your home when you have air in your pump. And you need to purge it, you need to take out the air, otherwise the work the pump does will not compress the water, but compress the air inside. So this is a problem. We don't have pumps that can pump two-phase fluids effectively. The second problem arises in the turbine. Turbines are devices that rotate at high speed, 3600 RPMs. So we have our 60 Hz line, and because recall that we are trying to get some work done here, and usually that work is used to produce energy, electric energy. So the tip of the blades are very high speed, especially the last ones, since we need to accommodate expanded vapor. The rotor will be bigger, so we can get problems, because if we have two phases, which we have all along this line, because the droplets of liquid will imprint on the blades, and they will create corrosion and wear. We can see here corrosion due hits by water. So we could try to move this cycle up, and then we will have what we call supercritical cycle. Problems rise in this part now because we need to transfer heat at variable pressures, and we give up our isothermal. So we will try to move this in a fashion to get out of the problems that we get. So we are going to move this in this direction, this in this direction. So now we have one phase for the pump, and since we have an isentropic turbine, we're going to have one phase for the turbine. This will give us some problems, because now we need to accommodate this. Remember that the isobaric consumed like this is not to scale. So now we have to pump water to the pressure of the boiler. Then we have subcooled water here. We need to add heat, evaporate, and along the same pressure we are going to have superheated vapor. So let's say that it's this way. Remember, it's not to scale. And then we're going to have the expansion. Okay, this is how our we're going to accommodate, or we're going to modify the Carnot cycle in order to get a practical cycle, and we call this the Rankine cycle. You can see here, much better done. This same cycle that we have our pump that pumps liquid water onto the pressure of the boiler, then we add heat until we vaporize it and then superheat it. We let this vapor go to a turbine where it expands and we have all this work, and then we condense it to have it all over again. Here we have the same cycle, and once you can see the arrows, we can just draw one in which we have the basic components: pump, boiler, turbine, and condenser. And we call this the simple ideal Rankine cycle. And we said it's ideal because we do not involve any reversibility. The pump is isentropic. We don't have any pressure drop in the heat exchangers nor in the connecting pipes. And we have an isentropic turbine. Any of these assumptions that we violate, and then we will not have the ideal Rankine cycle, but the actual or real Rankine cycle. And notice that we said here boiler, and but we don't specify how we're getting this Q in. And there are a number of ways. We have nuclear power. We could have coal or natural gas, and we can get by solar power our energy, the energy that we need to vaporize. This water, here is not pollution, is water vapor from the cooling tower. You can see here something very interesting. Since we need to condense, we would like to have a source of or a reservoir that we can use to reject all this heat, and usually we have rivers, except in Mexico. You can see that every power plant is not near a river. Other case will be for solar power, usually where you have plenty of solar power deserts, so you don't have water there, so you need to treat it differently. We need to have some water and take good care of it, and we use a cooling tower, just the ones like we see here. Okay, for every one of the processes in the cycle, we are going to use first law analysis. We should recognize that each of the processes is an open systems. An open systems is we have an input and outlet of mass. We also have either work or heat interaction, but the fact that it has mass crossing its boundaries of the surface of control, it's an indication that we have an open system. So this is the first law of thermodynamics for open systems in its more general form. All the heat interactions either in or out, plus the work interactions in and out, plus the mass interaction, the mass flow in or out, times the associated energy that goes with this mass flow. It is equal to H enthalpy plus kinetic energy, V squared over 2, plus potential energy as a gravity times Z. All of this equals the change of energy inside the system with respect to time. So we're going to make some assumptions to simplify this first law. And the first assumption is that we have a steady state. All of the processes that we're analyzing in the Rankine cycle can be considered steady state because the energy is not changing inside the volume with time. The second is that we can neglect kinetic and potential energy. This is reasonable for all of the processes, and the only one that might be important to consider is in the turbine, the kinetic energy, but we will see that it's not that important. For time's sake, we are going to use only one inlet and outlet. When we describe the enhancements to the Rankine cycle, when we describe open feed water heaters, we are going to see that we have more than one inlet and one outlet, or we can have the same for the turbines. So if we apply these simplifications, we can rewrite our first law analysis just as the heat in or out interactions plus the work in and out interaction. That's all the work or all the heat that can go in or out the system, plus the mass flow rate, and this time we are only writing one mass flow rate because we have only one inlet and outlet, and since we don't have any accumulation, the same mass that goes in should go out times the enthalpy difference, it's equal to 0. So for each of the processes, we are going to start from here. So our first component to analyze will be process 1 to 2, that is an isentropic pump. Recall the diagram, the TS diagram that we defined, and for this pump we can see that we don't have any Q interaction, we don't have any heat going in or out of the pump, so we cancel this term. Second one is that the pump is a device that need work in to perform its function, so we don't have any work out. We can cancel also this term. Then if we just rewrite what we have, we can see that the working, which will be the work of the pump, plus the mass flow rate times the enthalpy difference, should be equal to 0, again because this is a steady state for the isentropic pump. If we solve for working, we could see that we have just working is equal to mass flow rate times the temperature, the enthalpy difference, that is the enthalpy at the end minus the temperature at the beginning, so enthalpy 2 minus enthalpy 1, and the units are kilojoules per second or kilowatts. If we divide this by mass, we are going to have the specific work of the pump, and this will be just the enthalpy difference, and the units will be kilojoules per kilogram. State 2 is an subcooled liquid, so we don't have any tables to find subcooled liquid. So what we usually do is we solve this equation for H2, and we are gonna assume some make a simplification to get the work of the pump, which is the working, and this work of the pump will be equal to the specific volume, state 1, which is saturated liquid, times the pressure difference. Recall that liquid is incompressible. Liquid is incompressible, so the volume is the same along the process. Now for the boiler, we start again with the same equation, and we have process 2 to 3. So we don't have any work interaction. The heat in the boiler, we only add some heat, so we cancel this term. And since the heat that we are adding is the heat goes into the system, we are also going to cancel any heat out. We can certainly have it, but that's not what we would like. That would be the case of a poorly insulated boiler, and that heat out will be loss of money. Okay, so at the end we will have again HQ in is plus the mass flow rate times the enthalpy difference will be equal to 0, and the same as we did with the pump, we solve for Q in. So Q in will be equal to the mass flow rate that we have in our system times the enthalpy difference. And please be aware that the mass flow rate that we are taking in this system is exactly the same mass flow rate that we have in the pump, because we are talking about the closed system. So again, this is kilowatts, and if we divide by mass flow rate, we're going to get a specific heat, the heat per unit of kilogram that we need to add to the water in order to take it from state 2 to state 3. And this is in kilowatts, in kilojoules per kilogram. So these are the two ways that we are defining. Now we get to the third component, which is an isentropic turbine. In our diagram is process 3 to 4, and the first assumption is that we don't have any heat leaks. We don't have any heat interactions, either in or out. Again, if we have Q out, that means a poorly insulated turbine, and that heat that is going out is lost work. The turbine is a device that gives us work, so we don't have any work-in interaction. So rewriting this, we have the work out that, since it's going out of the system, has a negative sign, plus the mass flow rate times the enthalpy difference, H3 minus H4. Notice that we have every time defining H in minus H out, and the inlet of the turbine is state 3, while the outlet of the turbine is state 4. So similarly, we are solving for workout, and workout will be the mass flow rate times the enthalpy difference. If we divide again by mass flow rate, we will have the specific workout, and this is a work out of the turbine, and will be just H3 minus H4. Workout, the first expression will be in kilowatts, the second expression will be in kilojoules per kilogram. Let me just write that for you, so you'll remember that every time that we have the dot on top, capital letter, means that is a rate form. That means that is a per second, per time basis. So it's kilojoules per kilogram. This one, kilojoules per second, sorry, and this is kilojoules per kilogram. Now, finally, for the condenser it's a process 4 to 1, and it's a process that we use to condensate the steam so we can start our cycle again. So we don't have any work interactions, we only have heat out. We don't have any heat in, because that heat in will be an inefficiency, since we're going to need more energy to take it out from the water. So only Q out, and again Q out is has a negative sign because it's leaving the system, and plus mass flow rate times the temperature difference, the enthalpy difference. Solving for Q out, just to leave it directly, we have Q out equals the enthalpy difference times the mass flow rate. Just let me stress again that mass flow rate is the same mass flow for the pump, the boiler, the turbine, and the condenser. We have a closed system. If we divide by this mass flow rate, we'll have the specific heat leaving the condenser, and will be just equal to the enthalpy difference. H4 minus H1. Again, the first one is kilojoules per second, while this is kilojoules per kilogram, being in a specific heat living. Okay, well, this is the derivation of each of the energy balance for each of the components. In this slide, you can see them summarized just as you have it in your book, but you already know where they are coming from. We started from the first law for open systems, so for steady state. At the pump, we assume Q 0 for interaction. For the boiler, we assume no heat. Please take a look at these animations, and maybe they can help you to understand better. Thank you.